Welcome everybody to the Algebra 2 Chapter 7 review video. Hopefully you've all got your review guides right in front of you, and you've already checked your work with the key that was posted online as well, the PDF that was on our Haiku page. So, this chapter, there were a lot of situations where we had quite a bit of writing to do, right? The adding and subtracting, multiplying and dividing of rational expressions. It took some time, so we want to be as efficient as possible with these problems. And really, we come to find that the graphing problems from section 7.2 that seemed so cumbersome at the time are actually some of the faster problems that we'll be able to do when we actually sit down to take the test. Now, if you're going through this review and you're thinking there's no way I could do a test like this in a 50-minute class period, rest assured that there is a multiple choice section that helps out a little bit with the time management, gives you a little bit more guidance in how you structure your problems. Yeah, we want the review to be really comprehensive, so it's giving you more of a look at anything that could show up on the test than will likely show up on the test. So if we have, 4 adding and subtracting problems, there might only be 3 on the test itself. So don't be worried about time management, but we do want to use this as an opportunity to be as efficient problem solvers as possible. So let's get started. All right, so the first section opens up with multiplying or dividing. There will be, I believe, 3 of these on the test itself. I don't quote me on that, but you can see we've got them expressed in different ways. We've got 1 multiplication problem and 3 division problems. So for the first one, the multiplication, all of these we considered our trains, right? We want to set up our train cars and then see what cancels out when we multiply across the top and across the bottom. So for question 1, I'm just going to go through and just at a glance factor anything and everything that I possibly can. I want to set up all those train cars and then connect them all together. So in the top left here, I notice I can factor a GCF of x out, and I'm left with 2x minus 3. And then if I keep going across the top, I've got a trinomial. That's no sweat. Magic numbers, x plus 3, x minus 2. We'll factor that. In the denominator of that first expression, I do have a difference of squares, x plus 3, x minus 3. And I have another GCF, a 3x times an x minus 2, that I can factor out for the denominator of that second fraction. Okay, so we have all of our train cars established. Let's see what we have across the numerator when we hook that up. I've got x times 2x minus 3 times x plus 3 times x minus 2. Okay, remember we hooked it up. It's all one big fraction now. We multiplied across the top. Now across the bottom, x plus 3, x minus 3 times a 3x times x minus 2. Now that loose 3x is just kind of floating there. I want to be sure that I show that with a multiplication symbol so I don't lose it in the jumble. Or ideally what I would have done is written that 3x, if I recognized it, written that out front. All right, now what cancels? I'm going to show all the cancellations in the green marker here. So what factors are going to be multiplied in to both numerator and denominator and thus canceled by the division of the fraction? Well, let's notice right away we've got an x minus 2 factor, that cancels. And I've got an x plus 3 factor, that cancels. And then what some people will not notice is there's a loose factor of x. It's multiplied into the top and bottom. The division cancels that out. So my final answer is simply 2x minus 3 over what's left in the denominator. We still have this 3, okay, and then times x minus 3. Now, it's very tempting to want to cancel out x minus 3 or just the negative 3's, but remember, we cannot cancel those. They are not multiplied into top and bottom. They're just merely added in. So this is our, this is our final answer. For problem number 2, here it is division. So that means I need to multiply the first fraction by the reciprocal of the second. So I'm just going to make a note off to the side. I don't want to have to rewrite the whole thing. Again, I want to be as efficient as possible. So across the top, I'm going to have this 2x cubed y squared times the denominator down below. Remember, I'm going to flip that second fraction. So 2 times 14 gives me 28. X to the third times another x, x to the fourth, and y squared. I'm not multiplying in any more y's. And then there is a z being multiplied in. Okay, now let's look at the denominator. It's going to be 4x to the fourth z times, remember I'm flipping the second fraction, 2xy. So I get 8x to the fifth y z when I multiply all those terms together. And they're not factors in parentheses, so we just write that multiplication as those terms being right next to each other. Okay, what cancellations do we have? X to the fourth will cancel out every single x in the denominator except for one of them. Likewise with y squared, that will cancel out the y in the denominator, but it will leave one y in the numerator, and both z's will cancel out. And I am going to simplify this fraction. 28 over 8, I can divide top and bottom by 4. I get 7 over 4. And as far as variables are concerned, I'm left with a y in the numerator and an x in the denominator. 7y over, I'm sorry, that should be 2x. Divided them by 4. There we go. For number 3, again, I'm going to flip, so I'm going to show that. I notice that it is a division problem, so I know I'm going to have to multiply by the reciprocal of the second. Again, let's set up some train cars here so we can hook them up and cancel, simplify. Nice little trinomial, x minus 3, x minus 6. Underneath, it looks like a difference of squares, but because of that x that's there, all I can do is take a GCF of x out. Okay, what's this going to factor? Well, plus 4 plus 2. Magic numbers factoring. And up above, I get a minus 3 plus 2. And yeah, there are a couple things that look like they could cancel right away, but again, I want to save that for that when I connect everything together, use the reciprocal and everything, make sure I don't cancel something that really doesn't end up canceling. So across the numerator, I'm going to have my first numerator times the second denominator, since I'm multiplying by the reciprocal, all those train cars, x minus 3, x minus 6, x plus 4, x plus 2. Okay, again, connecting up, making this huge fraction. Across the bottom, I've got x times x minus 4 times x minus 3 times x plus 2. What cancels? Minus 3 and minus 3, plus 2 and plus 2. So my final answer, and you are allowed to keep this all factored out if you want. I'm going to write it underneath here to save room for number 4. Got my little recording window in the way. X minus 6 times x plus 4 all over x times x minus 4. And that's it. Those factors have to match perfectly in order to be able to cancel them. So it's tempting to cancel out x plus 4 and x minus 4, call it a negative 1, but we cannot do that. The only way that could happen is if we could take a GCF of negative 1 out of one of those factors, again, to make them match perfectly, and we can't do that here. Lastly, number 4, before I do this, I want to make sure I know where the big divide is. So I see that I have one fraction divided, across that big divide, the bottom fraction. So what do I have factoring in the numerator? Well, if I take a GCF of 3 out, make a little arrow here, then I'll have x squared minus 25, and that's not factored all the way. That's a difference of squares. So this is actually my factored numerator in the numerator. Okay. Down here, I can take a GCF of 6x out, and I'm left with an x plus 5. All right, so what am I setting up as a division problem? Well, let's see. I've got 3 times x minus 5 times x plus 5. Oh, I don't know if I gave myself enough room. That didn't really help much. Okay, and that's over 6x times x plus 5. Okay, and I'm going to be dividing by, well, here I can take a GCF of 4 out. I'm left with an x minus 5. And my denominator, I can take a 9x out, and I'm left with x plus 5. A lot of GCF work in this problem. Remember, to divide two fractions, I'm going to multiply by the reciprocal of that denominator fraction, so that gets flipped. So I'm also multiplying in 9x times x plus 5 in with that numerator after I flip and combine them together. Likewise, this 4 times x minus 5, that gets multiplied into the denominator because when we take that reciprocal, it will actually become a part of the denominator. So is there something that we can cancel right now? Absolutely, there's quite a bit. X plus 5, x plus 5, x minus 5, x minus 5. Let's see where we stand. Across the top, now I just have 27x. Ooh, and actually, timeout. There's a loose x in both numerator and denominator. Those cancel out. So my numerator is just 27 times x plus 5. And the denominator, everything canceled except 6 times 4. That's 24. And we can clean that fraction up. Divide top and bottom by 3. I get 9 times x plus 5 all over 8. Again, quite a bit of writing on this first page. There's a lot of factoring to do and a lot of canceling. And you can see based on the video, we spent about 10 minutes just doing these 4 problems. You can bank on about that amount of time to get through those problems on the test. So be sure that you're working as efficiently as possible. All right, for the second grouping, here we are adding and subtracting rational expressions. That means we need a least common denominator. So if I look at number 5, I've got a denominator that's 2x, and I'm trying to add to that a fraction whose denominator is x minus 2. Well, my least common denominator I'm going to get is by multiplying those together, 2x times x minus 2. Okay, so we're looking for the missing piece. That's what we're multiplying in. X minus 2 is missing from the first fraction's denominator, so I'll multiply that in top and bottom. And from the second fraction, I'm missing the factor of 2x, so I'll multiply that into top and bottom. Just set up that least common denominator for the whole thing. Okay, now across the top, that's where this addition actually takes place. I need to FOIL over here and distribute the 2x on the right. So if I FOIL that out, I'm going to get x squared minus 3x plus 2. Then comes that big addition happening in the middle. Then I will have 2x distributed in. That's 2x squared plus 2x. And that's all happening over our common denominator. We're just going to leave that factored out. All right, let's combine like terms in our numerator. I've got 3x squared minus 1x plus 2. And that's all over that common denominator again. And to see if this would simplify, we would try and factor the numerator, see if I could get a factor to match in the denominator. And in this case, we cannot. There's no way to have two numbers multiply to be positive 6 and add up to negative 1. So this one is done. Problem number 6. Well, let's set up our least common denominator. I see an x plus 1 denominator and x minus 3 denominator. My least common denominator will have both of those factors. Didn't really plan ahead there. Ran out of room. Okay, the first fraction is missing the x minus 3, so I'll multiply that piece in to top and bottom. And second fraction is missing the x plus 1 factor, so I'll multiply that in top and bottom. And I've got a couple places to distribute before I add those numerators together. Get x squared minus 3x, then my big addition, 2x plus 2, again, all over that common denominator. And if we combine like terms, x squared minus x plus 2, once again, over that common denominator. Okay, and once again, that numerator, there are no two numbers that multiply to be 2, and they also add up to a negative 1. It just doesn't happen. But we would obviously look to try and factor that if at all possible. That's the only way we could simplify it. All right, number 7, same routine. I've got a factor of x minus 2, factor of x plus 3 making up my denominators, so the least common denominator between the two has both parts, x minus 2 times x plus 3. Well, the first one's missing the x plus 3 factor, so I multiply that in top and bottom. And the second fraction's missing the x minus 2 factor, so again, multiply that in top and bottom. And thankfully, again, all we need to do is distribute, but we want to be careful. This time it's a big subtraction happening in the numerator, and that negative will distribute. So I've got 3x squared plus 9x, then a big subtraction, 4 times x minus 2. Okay, and if I were you, I would put everything that came from the numerator, the second fraction, in a set of parentheses just to be sure I don't miss a negative sign distributing. Okay, but again, that's all happening over our least common denominator. All right, so I've got 3x squared plus 9x, and then I'll have a minus 4x, and I'll have a plus 8 all over that lowest common denominator. And the last thing I would do to simplify is just combine like terms in the numerator. So instead of plus 9x minus 4x, I would write plus 5x. And I'm just erasing this and rewriting it for sake of space. Okay, again, 3 times 8 is 24, positive 24. No two numbers will multiply to make that positive 24 and add up to positive 5. We are finished. And weirdly enough, number 8, one of the easiest of these 4 problems, I noticed something factorable right away in that right-hand denominator. It's x plus 2x minus 2. Hey, and I've already got an x minus 2 piece over here. My least common denominator is x plus 2x minus 2. And I only need to adjust the first fraction. That needs the x plus 2 factor. The other one already has the common denominator. Sweet. So if I distribute and then carry out my big subtraction, I get 2x plus 4 minus 8 all over that least common denominator. We combine our like terms. That becomes 2x minus 4 all over that common denominator. Ooh, and we can take a GCF out of the numerator. We can simplify this. 2 times x minus 2 all over x plus 2, x minus 2. And we get that cancellation that we were hoping to see actually happen. Final answer is 2 over x plus 2. All right, now all 8 of these problems that we've just done, that covers the first page of content on the test. And remember, the test will have fewer problems in this, but I hope we can appreciate how much writing and how much time it takes to get through these first ones. After this, the pace should quicken. So don't lose heart at the fact that it's taking a long time to get done with the first page. That is likely to happen. So the pace will quicken, and we should have much less trouble as we move on. All right, next, to open up the chapter, we talked about variation. And number 9 says, if y varies directly as x, and then we're given a condition, y equals 4 when x equals negative 2, what is y when x equals 30? Well, remember, a direct variation means that our y value is equal to some constant times our x value. So if y equals 4 when x equals negative 2, I can find that k value, the constant of variation. In this case, k equals negative 2. Right? I would divide both sides by negative 2, just solve for k. Now I can answer the second question. What is y? I know my k value is negative 2 when x is 30, so I plug it back into that direct variation formula, y equals kx, and I get negative 60. That's my answer. Number 10, the distance a car can travel on a certain amount of fuel varies inversely with its speed. So the distance is the output, that's like our y value, that equals the constant of variation over the speed. Remember, an inverse variation is where we see a fraction. Instead of k times our input, now it's that constant divided by our input. All right, and notice that they're kind of throwing us for a loop here. They throw some extra numbers in there. The gallons of fuel have nothing to do with the variation. Distance varies with speed. So the 10 gallons has no bearing on this problem whatsoever. All right. So if our distance is this constant over s, let's use the given information. Okay, a distance of 336 miles is traveled, some constant divided by a speed of 50 miles an hour. My k value is going to be found by multiplying both sides by 50. It's 16,800. Now let's actually answer the question. How far, trying to find the distance, could the car travel? Well, we know that constant of variation is 16,800 if it's going 60 miles per hour. So now the speed, the input, is 60. And a quick trot through the calculator, we type that in, we find 280 miles to be the answer. Here, since it is a word problem with units given, our answer should be units. How far can you travel going 60 miles an hour? Oh, 280. Well, 280 what? You know, give the units, answer the question. And lastly, I did jump from problem 10 to 14, so you may have to flip through a page on the review guide to get to number 14. I thought it fit better with these problems than with others. Alice can paint a room in 8 hours. Her assistant can paint the same room in 12 hours. How long will it take the two of them to work together? All right, well, the key is to think about how much each person is doing per hour. Okay, so for Alice, she does 1/8 of the room per hour. So 1/8 times however many hours she's working, that tells us how many rooms she's painted overall. Plus, her assistant, every hour will do 1/12 of a room, again, times however many hours she is painting. All right, well, the two of them combined, I want them to paint one room. So I'm just solving for h. How many hours are they both working? If those are their respective rates per hour, you know, we've got this nice little equation set up, and it requires some common denominators. In this case, the least common denominator is 24. So 1/8 is 3/24 h plus 1/12. That's 2/24 h. That equals 1. If I combine those together, that's 5/24 h when they're working together equals 1, and I can solve for h, the number of hours. Simply divide away 5/24, that means multiplying both sides by the reciprocal. I get h equals 24/5 hours. And that is an acceptable answer, but if anybody is looking for a point of extra credit, we can be more specific than that. Right? 24/5 is equal to 4 4/5. That means it's going to be 4 hours and 4/5 of another hour. And 1/5 of 1 hour is 12 minutes. So if I have 4/5, that would be 4 sets of 12 minutes. That's 48 minutes. So if you have an answer that says 4 hours, 28 minutes, you're more specific than just that general fraction. You can expect a point of extra credit coming your way because you've gone above and beyond. Okay, and obviously you can tell the pace has quickened when we get to these variation problems. Obviously not nearly as much writing when we don't have to factor everything in sight. So take heart in the fact that this does speed things up. All right, 11, 12, and 13, the section where we have to, now we're going back a little bit, so I apologize if you have to flip pages here. Now we're going to go back and actually solve these equations. And number 12 is one that's jumping off the page at me just because it's so simple. It's one fraction equal to another fraction. I apologize for going out of order, but I just want to get this one done because it's so fast. When it's fraction equals fraction, let's cross multiply that. Okay, so I've got x times x minus 2. That means I will have to distribute x squared minus 2x. And then my other diagonal gives me 3 times 5, 15. It's a trinomial, so I better get it set equal to 0 before I solve. And it does factor x minus 5, x plus 3. And I find my solutions are positive 5 and negative 3. Now, before I box this up, I do want to go back and check, would any of those solutions produce a 0 denominator? And they will not. So I do have both of those as acceptable answers. And if I wanted to, double check, I could type the left-hand side, the x over 3 into y1, the right-hand side, 5 over parentheses, the quantity x minus 2, and just see in the graphing calculator how many places do those intersect. And those graphs actually do intersect in 2 places. All right, so let's go back to number 11 now. This one, if you can believe it, is actually a longer problem than number 13. All right, there go the bells. Now, to solve rational equations, we want to establish the least common denominator among all involved parties here. So I've got a piece that's an x plus 4 as a denominator, a piece, and when I say piece, I mean factor, that's x minus 3 as a denominator, and on the right-hand side, it's just 3 over 1. It has no denominator visible from the onset. So my least common denominator is going to be x plus 4 and x minus 3. Now, once I set this up, let's just go through a quick example of why this works. If I had something like 5/3 minus x over 3 equals 2 over 3, what I could do to solve that is multiply both sides of that equation by 3, and then the denominators would simply be gone. So once I have the same denominator in all 3 places, all of my work is essentially happening in the numerator, because we could essentially just multiply both sides by that denominator and they would all cancel out. So that's my reasoning behind this and why I'm able to move through these so quickly. So for number 11, what's the only thing missing? Well, it's the x minus 3 factor. So I'm going to multiply that in. And again, remember, all the action is happening in our numerator. The second fraction, all that's missing is the x plus 4 factor. So I jot that in. And on the right-hand side, it's missing both pieces. So I'll have to multiply in the x minus 3 and the x plus 4. And I've made all of the adjustments to set up that common denominator. Now I can turn my attention to just what's happening in the numerator. I've got 6 times x minus 3. Let's distribute. Big minus, I'm going to put this in parentheses, 2 times x plus 4. That's 2x plus 8. And again, that negative will distribute, so I want to be careful about that. That equals 3 times, well, let's see, what's this going to make if I FOIL that together? X squared plus x minus 12. So I'll have 3x squared plus 3x minus 36. Because I not only do I have to FOIL, I have to distribute that 3 as well. All right, so let's build this equation, right? We don't worry about the denominator anymore because we know that it would just cancel out anyway. Why bother writing it every single time? That's a lot of wasted effort. So I distribute the negative. Let's combine some like terms. Okay, we can definitely see a trinomial forming, so we want to get it set equal to 0. I subtract over the 4x, add over the 26, and now I have something to factor. What multiplies to be negative 30 adds up to negative 1. Hey, this works. It's negative 6 and positive 5. It was a 3x squared. I need to divide out that 3 and simplify if possible. So those are the magic numbers that would go into factors, but if I were solving the factors, I would simply switch the signs. So my final answers are going to be positive 2 and negative 5/3. And again, before I box that up, I just want to look back up at the top. Are there any x values that would produce a 0 denominator? Those are the ones that we can't have. And looking up at that, no, there aren't. So both of these answers are acceptable. And again, we could check by typing in the left-hand side. All of that, we want to be careful with grouping, of course. But typing all that in as y1, the right-hand side, y2 would just equal 3, and see how many times they intersect. And lastly, number 13. Okay, I do see something factorable. I want to attack that right away. It's just a magic numbers situation there to factor that trinomial. And hey, look at this. I have very few adjustments to make on the left-hand side. My least common denominator is going to be x plus 3 times x minus 2. So let's make those adjustments. Multiply in an x minus 2, multiply in an x plus 3, And then on the right-hand side, it's already got the common denominator. No adjustments necessary. So let's go ahead. We know all the actions happening in our numerator now. I will have 5x minus 10 when I distribute, minus, okay, and I'm going to put this in parentheses because that negative will distribute, 3 times x plus 3, let's go ahead and distribute that now, 3x plus 9 equals 5. And look at how simple that became just by taking the time to set up our lowest common denominator from the beginning. All right, so let's combine like terms and distribute here. I'm going to distribute that negative. I've got a 5x and negative 3x. That combines to make 2x. Got a negative 10 and a negative 9. That's negative 19 equals 5. And welcome back to Algebra 1. Add 19 to both sides and divide by 2. X equals 12. Quick run back through. Does that 12 produce a 0 denominator? No, it does not. X is an acceptable solution. All right, that does it for all of the intensive algebra. The rest is just dealing with graphs. And hopefully we got lots of practice from that 7.2 big packet worksheet that we had. You know, so we rattled through, we had our steps, our 3 zeros, our big X test, maybe some freshman graphing to produce these graphs. Let's get after it. So the first thing we need to do, does anything factor and cancel? So here I've got x plus 4 times x minus 2 in my numerator. Denominator is x minus 2. Hey, we get a cancellation. That function's really the line x plus 4, but something produced a 0 over 0 along the way. When a factor cancels, it produces a hole in the graph. So what x value would cause that 0 over 0? What x value comes out of that canceled factor? It's a positive 2. And I want to find the y value that goes with it. So I'm going to plug that into our simplified function over here. It actually works. It doesn't give us a 0 over 0. I get an output of 6. So the 0.26 on that graph is a hole. I'm just going to mark that with an open circle right now. Okay, next we have our 3 zeros. So looking at the vertical asymptotes, that happens when the denominator equals 0. And again, we've already simplified it. What would make the denominator 0? Nothing. There's no denominator. So there is no vertical asymptote. The horizontal asymptote, we're looking at the big X test there. What happens when X is huge? Well, the numerator takes over. And if we look at the original function, we can see the numerator had a higher degree. So the numerator takes over. That is indicative of a graph with no horizontal asymptote either. The x-intercept, that's what happens when the numerator equals 0. Well, my numerator is just x plus 4. What would make that 0 if x were to equal negative 4? So the point negative 4, 0 is our x-intercept. And our y-intercept happens when x equals 0. So if I plug in a 0 for x, I'm just left with 0 plus 4, or 4. So the point 0, comma 4 is my y-intercept. Okay? Now, the domain of this graph, we have enough points. We know, based on the fact that it made a linear function, that we're going to have a straight line graph here with a hole in it. My domain is going to consist of all x values such that x does not equal 2, the x-coordinate of that hole in the graph. And my range will be all y values such that y does not equal 6, the y-coordinate of the hole in the graph. Okay, and we may want to take the time on this first one, especially if we're looking back at our notes. We may want to say, hey, vertical asymptotes, where does the denominator equal 0? Horizontal asymptote, that was the big X test. We're looking for what takes over. The x-intercept, that's where the numerator equals 0. What would 0 out the numerator? Y-intercept, what happens when x equals 0? If we know those 4 things, we can really rip through these problems in a hurry. Okay, number 16, well, it's not factorable, so I don't get any cancellations or a simplified function, unfortunately. That means there's no holes in the graph, though, to worry about. The vertical asymptotes, what x value would make the denominator 0? Well, that's if x were to equal -1, and I need to write that as an equation, x equals -1. It is a line on our graph. The horizontal asymptote, that's the big X test. Well, look at this function. The degree of the numerator is 1. The degree of the denominator is also 1, so there is no takeover there. So I look at that 3x and that x. What's leading the numerator? What's leading the denominator? And I find that I get 3/1 for those coefficients. Y equals 3 is my horizontal asymptote. My x-intercept, what would make the numerator 0? Well, if x equaled 0. So the point 0, 0 is my x-intercept. My y-intercept, if I plug in 0 for x, I get 0/1. Hey, that's 0. So 0, 0 is also my y-intercept. And if I look at my graph, I can tell that, hey, once the graph passes through this point that I know at the origin, it's going to be drawn towards the asymptotes, both vertical and horizontal, as it moves away from that point. I don't, however, know what's happening over here to the left of the vertical asymptote. That's where I need to use a little bit of freshman graphing, make a tiny table of values, and just choose an x value that's over in that region and keeping it close to that vertical asymptote. So I'm going to choose -2. Now, if I plug in a -2, I get -6/-1. That's +6 for an output. So the point -2, 6 is also on my graph. And again, once I move away from that point, I'll be drawn toward the asymptotes. The graph will approach them. The domain, the only thing that would disrupt this function is the vertical asymptote. So x can be any x value it wants except for -1. And for the range, similarly with the horizontal asymptote, all y values such that y does not equal 3. When you actually sit down to take the test, there will only be 2 of these graphing problems. But again, we wanted to give you a full range of concepts to study. What are the different types of graphs that we have seen throughout the chapter? So here we are at our final question on this review. All right, I notice right away that, hey, nothing cancels out, nothing factors, so there are no holes in the graph. Vertical asymptotes, what would make the denominator 0? Well, if x were to equal -5, that would certainly make the denominator 0. Let's go ahead and put that in right now. The horizontal asymptote, if I conduct my big X test, what's taking over that function? The numerator is degree 0. The denominator is taking over. It's degree 1. If the denominator takes over, y equals 0 is our horizontal asymptote. And we covered that fully in section 7.2, why that makes sense. Our x-intercept, what would make the numerator equal to 0? Well, there's no x value that would do that. So there is no x-intercept. And that makes sense because we have an asymptote there. That's very likely. The y-intercept, if I plug in a 0 for x, I'm left with simply 2/0 + 5. That's 2/5. So the point 0, 2/5 is that y-intercept. Okay, and I'll plot that in about 1/4 of the way up. And I have enough over here to draw in that graph approaching the asymptotes passing through that point. But yet again, there's a region on the left where I don't know what's going on. Always go back to fond memories of freshman year, making an XY table of values to take care of that. The x input that I'm choosing is going to be a -6. Again, staying close to that vertical asymptote, but being on the side of it, in this case on the left side of it, where I don't know anything about the graph. If I plug in a -6, I get 2/-1, which is -2. So -6, -2, another point on the graph, and I can draw the graph in to approach the asymptotes from there. Domain and range, my domain is all x values as long as x does not equal that -5 where our vertical asymptote happened, and our range, all y values such that y does not equal 0 where the horizontal asymptote occurred. All right, so there you have it. I've gone through the complete review with you from start to finish, and you can see it took me just about 40 minutes or so, just taking the time to explain every single step along the way. So again, I stress that if we're worried about time management on here, it is definitely a manageable test. Remember, the actual test will have one fewer graphing problem and fewer problems at the start dealing with adding, subtracting, multiplying, and dividing. And you know, we fill that in with some multiple choice, and there will be a couple extra credit opportunities as well on this test. We covered one of them in this video. But again, as long as we've taken the time to prepare ourselves and be as efficient as possible, knowing what to do at the start of each problem, you should have no issues finishing this test on time. That does it for this review video. Good luck on this Chapter 7 test.